Good. So as I said, the change in position will be the final position minus the initial position. The average velocity is going to be the change in position over the change in time. And we made an important distinction between average and instantaneous velocity. Instantaneous velocity is going to be the velocity at a single instant in time, which we represent like this. However, unless you're in calculus, we don't ever do any actual computing with this. The main way in which we found instantaneous velocity was from the slope of a position graph. So if I have a graph of position versus time here, and I wish to know the velocity at time t1, then I would do it how? Draw a tangent line, exactly. And the slope of that tangent line is the velocity, the instantaneous rate of change. Acceleration we defined as the rate of change of velocity with respect to time. And the same kind of logic applies. If I have a graph of velocity versus time, and my graph looks something like this, and I wish to find the acceleration at this time t1, then I'm going to get myself a tangent line, and the slope of that tangent line is going to be the acceleration. Notice that it is very important to pay attention to what graph you're looking at. If you're looking at the graph of position, your slope is a velocity. If you're looking at the graph of velocity, your slope is going to be an acceleration. Along the way, we learned a very important fact, and that is that the acceleration due to gravity near the surface of the Earth is constant. And what is that constant value? 8 meters per second squared. In which direction? Straight down. Gravity always pulls straight down. Armed with the idea of acceleration, we then created for ourselves some equations that describe the motion of a particle when it is experiencing constant acceleration. And those three equations were V equals, everybody all together, nice and loud. That was mediocre. Delta X equals. It's a little better. Say it so that Ms. Prentice knows that you know it.
B squared equals the initial squared plus
2a delta x. Thank you. Somebody knows how to shout.
C.
Okay. And these are the three equations of motion. These apply to an object that is moving in a straight line, either back and forth or up and down. They also apply in 2 dimensions if we allow these quantities here to be 2-dimensional vectors.
What does that first word say?
Yeah, is that abbreviation for equation?
Equation, EQN. What is the difference between a vector quantity and a scalar quantity?
Vector has size and a direction.
Vector has a direction. How do we... What's the official word for size? Magnitude, that's right. Blake, stand up, show everybody your shirt, read it. Read it all up.
Team vector building robot with magnitude and direction.
Thank you. You can read it.
Wait a minute, what? Wait, can you show me? Oh.
Okay. In one dimension, how do we indicate the direction of a vector? Positive or negative, very good. In two dimensions, how do we indicate the direction? That's it. That's right. We use x and y components. How do I know to use, how do I know whether to use plus or minus or components? What do I look for in the question that would tell me? What do I look for in the question that tells me whether to use plus or minus or to use components? That's right. It's whether the object is moving in one dimension or two. And that's it. So you have to visualize the path in your mind. If the path is a straight line, then I can just use plus or minus. If the path is some kind of a curve, then I'm going to have to use components. Speaking of, our favorite kind of motion in two dimensions were the projectile problems. You guys remember these? And a typical kind of problem might be something like this. Tom chases Jerry on a table that is 2.0 meters off the floor. He slips and slides off the table with a speed of 6 meters per second. How far away will he land? I'd like for all of you to take about 3 minutes to answer this question. Go. It is a long time ago. This is why we review. Okay, and so in the interest of time here, hopefully all of you drew a picture. I'm showing that it's 2.0 meters high. And what is needed in order to solve the problem is an initial velocity in rectangular form. And my V0 is perfectly horizontal in this case because he is sliding off of the table. And therefore, I'm going to represent with components. How did I know components? Because I have a y direction that he's going to fall in and a horizontal direction that he's traveling. 2 dimensions, 2 components. So this is my initial velocity. And this allows me to set up equations of motion in the x and the y directions. In the y direction, what I'm looking for is how far away he is when he lands. So I'm looking for this guy right here. Specifically, I am looking for delta x. And what I know is that he hits the ground, which means he hits the ground when, here's the key, when y equals 0. That's exactly right. So I set up the equation of motion, delta y is equal to v0t plus 1/2 at squared. And the initial velocity in the y direction is 0. And the acceleration in the y direction is 9.8 meters per second squared. If it's okay with you, I'll call that 10. And the change in his y position, if you'll just stick this together, that'd be great. The change in the y position is final minus initial, or 0 minus 2, negative 2. If you had the delta y as 2, then you need to pay attention to direction. And this gives me t is therefore equal to the square root of 2/5, or the square root of 0.4. The square root of 0.4 is like 0.65, something like that. Somebody who got this, is that correct? 0.64. Okay. And now we're ready to take that time and use it to figure out the delta x. In the x direction, delta x again equals v0t plus 1/2 at squared. But I'm going to use the initial velocity in the x direction, and the acceleration in the x direction is how much? 0. That's right, because gravity pulls straight down. And so, since I already have the time that it takes for him to fall, then I know the amount of time that he's going to be traveling horizontally as well, and that's going to give me 3.8 meters as the distance that he travels horizontally, which is pretty far out. Practicing projectile problems on your own so that you can do those is a really good idea. So the ancillary things that happen with vectors, very often vectors came to us in two forms. What are those two forms?
Scalar and polar. I mean, polar and...
Polar and rectangular. And so everybody needs to know how to go from rectangular to polar and vice versa. The easiest is polar into rectangular. Here. And slightly more challenging is the rectangular into polar, because the formulas are a little more intimidating. And we also have to remember that there is an arbitrary adding of 180 degrees if x is less than 0. And students will often forget that small condition right there. In other words, the inverse tangent will only ever give me an angle on my calculator, will only ever give me an angle in quadrants 1 or 4. If I know already that my angle is in quadrant 2 or 3 because x is negative, then I have to add 180 degrees to it to make it right. Okay?
Is our exam going to be multiple choice, all short answer, calculator, no calculator?
Mostly short answer with some other multiple choice or true false kind of questions.
We're going to have a calculator the whole time?
Yes.
I have another question. How long is the test? Like, how many questions?
11 inches. It's put it this way, it's designed to take up about 1.5 periods if you're very comfortable with what you're doing, so that gives some people some buffer.
So it's like the equivalent of 2 tests.
Yeah, or 1.5, somewhere there.
Oh, so not even like, so like the amount of questions in 2 tests? Or 1.5 or less?
1.5 tests or so, yeah. Yep. Okay, let's see. Well, what causes an acceleration?
Push. Force.
Of course, that's exactly right. And that led us to Newton's laws and forces. Everybody needs to know Newton's laws by number. If your forces are 0, the acceleration is 0. Very good. Which means that the object will not move. Is that right? No. What does it mean? The object will stay with its current velocity, whatever that may be. It will not change its motion. Yes.
Can I ask another question before I forget?
Sure.
It doesn't have to do with this, but I just want to ask that when we ask like a week and keep fitting. When are you going to update your grades and deadline?
I did calc. I need to do. I did calc PC this morning, and I can do physics today or at after school.
Okay.
Yep. I think I can. I have to check and make sure that. Yeah, it won't have your latest labs in it.
Okay.
Okay.
The summer course we would max out the salary.
That's it. This is Newton's second law, possibly the most important of the 3.
And F AB is equal to negative BA, FBA.
Awesome. Wonderful. Newton's third law. For every action, equal and opposite reaction. We remember that forces come in action-reaction pairs, right? This led us to the all-important free body diagram. We're going to take an object here, a mass M, and it is going to have a coefficient of friction mu with the inclined plane right here. I'd like for all of you to draw a free body diagram for the mass M. Go. We don't know. What would determine whether or not the object would be sliding down?
Well, prerequisite question.
The amount of
Maybe
friction.
force.
Yes, and we know that because it has a coefficient of friction mu.
Oh, okay.
Good question.
Can you give us a way to remember which direction is theta cosine or something? Cosine
Yes.
Theta.
Parallel is always mg sin theta.
But I mean, like
Up and down,
how do you remember? How do you remember it? Like other than just memorizing it?
what goes with which one?
It's like-
What
it's like-
goes with
It's
the
pretty
normal
pretty easy to
force?
memorize.
Like which one goes with normal force and then which one goes with friction? Like sine always goes with friction and cosine always goes with
So one free body diagram could look like this. If I take and put it into components, I'm going to answer Heidi's question from the perspective of the 11th grade me taking physics, because I could never remember mg sin theta, mg cosine theta either. And what I finally did was I checked the extremes. If my theta is all the way at 0, just like that,
Yep.
then the parallel component should be 0, and the perpendicular component should be equal to mg.
Right.
And that means that this guy has to be the sine component, because the sine of 0 is 0, and the cosine of 0 is 1. So I would,
See, I'd have to remember that too.
it's like a guess and a check thing.
Yeah.
That's how I did it.
Yeah.
Another, you could walk through the angles here, but what I usually tell my physics students is just to remember that the parallel component is mg sin theta. If you have to figure it out, then I would do it like this. Here's a nice little triangle here. This angle's theta, whatever that is. So this is 90 minus theta, and then you can do the opposite adjacent thing with it. Okay? Good. This led us to all manner of analysis. The important thing that we had was frictional force. There are two flavors of friction, static and kinetic. Static friction occurs when the object is doing what? When the object is not sliding with respect to its thing. What important class of objects should not be sliding? Rolling objects, especially wheels, right? We do not want our wheels to slide, especially when they're on our cars, on our roads. And so rolling objects experience static frictional force. What the wheels do is not slide on the surface, but push off of it. And the static frictional force was interesting because it is variable. It can change according to how hard an object is being pushed. And therefore, we said that the static frictional force builds up to a maximum value of us times the normal force. We've been doing Fn for our normal force. Let me continue with that. I reverted back to old school for a minute there. Whereas the kinetic frictional force is constant. It is always mu k times the normal here. And this is for objects that are sliding. Which one is always larger than the other?
Static.
Static is always larger than the kinetic. Yeah. Yes.
So, since let's say something's rolling on the surface, right? It's static friction, right? And since the static friction is always slower than kinetic friction, why would you want something to roll instead of just sliding?
Friction serves two purposes. One is to slow things down, right? But the other is to provide grip. When I'm walking across the floor, I want my frictional force to be large enough so that I don't slip.
Right.
And it's the same is true with wheels. So the friction that we're talking about is not the friction of the bearings. We're talking about the friction of the wheel against the road, or in other words, the grip. We want that to be as large as possible.
I hate when like you're going around the corner and like it like
And you can feel it slide out from under you.
yeah,
That means you're going too fast.
or you turn the wheel.
Yeah. Hey, speaking of motion,
Just one more thing. You wrote the static friction is always lower than kinetic, but isn't there like one point where the static will be a little bit higher than the kinetic in terms of
yes, so if we look at a graph of frictional force versus applied force, and what we see is that the applied force and the frictional force will cancel each other out or be equal up to a maximum limit, and that maximum limit is us times the normal. And then immediately it drops down to the kinetic level right here.
so the static is not always lower than the kinetic?
Well, when I say that, what I mean is that us is always greater than mu k. The coefficient of static friction is always larger than the coefficient of kinetic friction. Okay, so speaking of motion, one of the things that we did was circular motion. And we did it in two gulps. The first thing that we looked at was velocity and acceleration in circular motion, and then very recently we've talked about angles also, right? So let's talk about an object experiencing constant circular motion. What does the word constant mean in this case? It had a specific meaning. What was constant about it? Nope.
Also the direction.
Nope. 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 Well, the circle is constant. The shape is constant, yes. But there's something else that makes it constant
The
circular.
fourth applied.
The gravity will always be.
Definitely not the rotation.
The diameter.
It's on radius.
Like
Are we glad we're doing this? Constant circular motion means constant
velocity.
speed, which is not velocity.
I know speed is not velocity.
Now, why is it constant speed but not constant velocity?
Because it changes direction.
It changes direction. That's exactly it. Okay. Speaking of, which way is the direction of the velocity of an object that is moving in a circle or any path?
Tangential.
Tangent. That's exactly right. All velocities are always tangent to the path of motion. It's true for circles. It's true for non-circles as well. If the object is moving with constant circular motion, which direction is the acceleration? Towards the center of the circle. That's exactly right. So that for constant circular motion, the velocity and acceleration always point like so. And in fact, the acceleration has a specific value. It is centripetal, and therefore its value is
R over.
Whatever answer you have, check the units and make sure it works out.
Acceleration equals velocity squared times r over something.
V over R
Square
squared.
over R.
Check the units and make sure that works. Does v squared over r work? That's gonna be meters
R over V squared.
over per second squared, meters squared per second squared, divided by meters.
I thought it was V
Does
squared
that
over
do
R.
square root
It's
of something?
It's V squared over R.
Ah! And one factor of meters cancels out, yep, that's an acceleration, all right, and that is the correct acceleration. The centripetal acceleration is v squared over r.
Bomb.
Question? No
Dang
question?
it, why did everything have two?
No question?
So it's squared over R.
It was like,
You're just making this check.
Yep, I was making you check. What's the difference between a centripetal force and a centripetal acceleration?
Force is pulling things, the force is pulling it in.
Ah, what value does it have?
It has to be something.
It's in newtons. It will be in newtons, so what value does it have? What's its formula? Mass times acceleration, so in other words,
NV squared over r.
mv squared over r. Exactly so.
Oh, I see. You're getting back.
It's like substitution. It is like substitution. Substitution makes the world go round, buddy.
Buddy?
Okay, that's good enough. We did plenty, and we'll pick this up again on Monday, assuming we have school.